We will have 2 sessions. The second one will be by Dr. Jay Kumar, starting at 4 o'clock. Right, we'll have a small break in between 2:10 to between 4:10, 4 to 4:10, maybe something like that, and then we'll start the next lecture. Some of you are struggling with Canvas, how to log into Canvas, because the exam will be on Canvas, materials are on Canvas. So what I would suggest is we will wait for some time after the class around 6 o'clock. Mr. Ramesh and Dr. Geeta, both of them are part of the EICT team here. They will make a demonstration along with Deepesh ji also will be there. So they will do a demonstration of how to access Canvas and resolve the problems also. We will also have a similar session on Monday also. I will also be there. We'll try to resolve any problems that are there. Right? Please follow the instructions that are given in the email. You can take it forward. Right? So look at the instructions. Try it. If you're not able to do it, there may be some other technical issue. We will resolve that at the earliest. So there will be a demonstration today at 6 o'clock, 6:10, whenever Dr. Jaykumar completes, and then you can take it forward. Right? So happy learning. We are about 250 members now. So ma'am, Nivedita ma'am, you can start.
First, am I audible and screen visible properly to everyone? Is there any issue? Audible. Okay. So I'm not using any headphone because I think this is better version in terms of audibility. I just changed it right now. Okay. Thank you. Thank you. I'll be louder. No issue. So great. Okay. So today I know that you are into Qiskit. So you are into the coding part, but we have to again come back a little bit. A quick recap I'll be giving first. Then I will share that what today is our agenda, what we are going to cover, which is again a part of the recap. Followed by quiz. First, I want to give answer to the quiz part. In quiz, you will be having MCQ questions, multiple choice type and multiple select type questions. 20 questions, 15 from multiple choice and 5 questions will be multiple select. Since here in this part, we are only covering the quantum physics, quantum mechanical postulates and all. So luckily there will be no numericals that you have to solve. But there will be theory questions based on the numericals or some of the math concept. That is for sure. Topics you can expect is whatever we have covered in all the 4 lectures. Whatever we have shared during the slide content, what is already shared with you along with during the 2 hour of session. So you have to cover both. Do not please only rely on the PPTs that have been shared. Okay. If needed, please go through the video lectures, which is already recorded for your understanding. But it is the same thing. And from the earlier lectures, lecture 1, 2, and 3, where we covered a bit of the wave-particle duality, that quantum physics part, superposition, all the quantum mechanical postulates. Today, we will be covering 3 very important postulates. They are the cloning theorem, teleportation, and dense coding. A bit of the quantum basic gates. I know that the quantum gates is not a part of your part of your curriculum for the QT-02, at least what I have covered, that much. It's a very, like maybe small existence it has, but still I have given a few questions just because first thing I will be covering today, and I already have covered in lecture 3. And secondly, I will be giving only questions from quantum gates, those which are related to the quantum mechanical postulates. Not very in-depth questions you are going to get. I'm not audible. Okay, yeah, and ICT is telling. Kindly check.
Hi, ma'am. Ashish this side. You're properly audible.
Okay.
My
Yes.
Yeah.
Thank you, sir. Thank you, sir. So I hope all of you have got what kind of questions we're going to get. 15 MCQ, 5 multiple select type, and what are the topics. Okay. So today, as I already mentioned, 3 very important postulates. These are left. I will be covering them. This is the primary section. Along with that, on the Hermitian matrix or the self-adjoint operator part is missing. Okay, that I will be covering maybe at the end or something. And a little more on the quantum gates. I guess I only had covered Hadamard and CNOT gate. Okay, as I can remember. So first I will start with a quick recap of Hadamard and CNOT gate, so that you understand that what is the position, how to map between the circuit as well as the matrix form of the representation of the quantum gates. Just a quick map between them I'll be doing. And then the remaining 3 to 4 quantum gates we will be first discussing. That is the plan. Then we will either jump to Hermitian or no cloning based on that outcome. Okay. I want to start now. All of you, please focus. So, first we have seen Hadamard gate. This is just a recap part, so I'll be little fast here. So Hadamard is used for superposition. We have seen it. So representation is something like this. And since now you are a bit well versed with Qiskit, I think it will be even more easier for you to understand. So this is how you represent it. You can drag the Hadamard gate from the library and you can directly see the implementation. I hope Jaikumar sir already covered this part. This is Hadamard gate, and how the matrix looks like. It looks like this: 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root over of 2. This is also called a Hadamard operator. Right? Now, whenever this is, we often write it in this way as well, taking 1 by root over of 2 as common. We often write it down in this way. Now, whenever Hadamard is applied on gate 0, so how it looks like, Hadamard is nothing but 1 by root 2, this thing. And whenever it is applied on gate 0, which is 1, 0, so 1 is for 0th position, it is on. So that is why it is 1. It represents 0th position. So if you just multiply them, it will become what? It will become 1 over root 2. And here also it will be 1 over root over of 2. You take it common, it is nothing but this, which alternatively also can be represented as this thing. So here for 0th position, it is 1, and 1th position, it is also 1. So you can write it down in this way. Right? So in short, Hadamard on gate 0 gives you 1 over root 2, gate 0 plus gate 1. Similarly, I will not do the derivation again. Hadamard on gate 1 is going to give you what? 1 over root 2 gate 0 minus gate 1. Considering gate 1 is nothing but this thing, 0 and 1. Just check the multiplication. It will ultimately give you 1 and minus 1. So that is gate 0 minus gate 1. Till this part, it is all okay, I guess, with everyone. And similarly, if you increase more, it will be more. For example, for a 2-qubit system, you don't need to really remember that part. So it just initially say it was 0 and 0. You have applied Hadamard on both of them. So here you have got 1 by root 2, gate 0 plus gate 1. And here also you have got 1 by root 2, gate 0 plus gate 1. And this is nothing but a tensor product, right? So it will be 1 by root 2, 1 by root 2. You can take it as common. Just take it, then it will be 0, 0, 0, 1, and likewise. So it's 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. So it's half 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Right? Where half, if you again just put it with as an amplitude to every of these 4 quantum steps, that means this is your what? This is your probabilistic amplitude for a 2-qubit system. But what is the probability? Then you have to make it a square. Then it will be 1 by 2 whole square, that is 1 by 4. So that means 25% probability of getting gate 0, 0, Similarly, 25% for QT-01, 25% for QT-10, and 25% for QT-11. I hope this part is clear. For 3 qubit, 4 qubit, 5 qubit, accordingly, you can just do the tensor product and you can get the output. I'm not going to show you in how Qiskit actually the quantum circuit is going to look like. I hope that is now okay. Or it's nothing but like something like that. Say H and H. Only this thing. Only this thing. If nothing is written over here, it's ultimately nothing but QT-0. If nothing is explicitly mentioned, we initialize it with QT-0. And if it is 1, we have to do something else. We have to apply a NOT gate on that respective qubit positions. Right? So that is done. Then we have seen the CNOT. CNOT is nothing but controlled NOT gate. Right? So it is represented like this. We have seen it. So it works like control and target for both. Control and kind of. Just a minute. Okay. So this is nothing but this thing. So 0, 0, it will keep it 0, 0. If it is 0, 1, this part is input and this part is output. And this is your input. So 0, 1, it will keep it 0, 1 itself. 1, 0, it will then make it 1, 1. And if it is 1 and 1, then it will make it 1, 0. I hope the logic is clear to everyone. What was the logic behind it? If control is 1, then only you have to flip your target. If control is 1, then only you have to flip your target. T is target, C is control. Okay? That is the thing. And if there is a 0 in control, you don't have to do anything. That was the CNOT gate. Now, first, next gate that I want to introduce here is a C-square NOT gate. Why? Because often you will be getting this direct gate. So it's very useful. So it's called a controlled NOT gate. From the name itself, you are understanding at least one thing, that there has to be a dependency with multiple control. It's a controlled NOT gate. So it's also called Toffoli gate. In this name, it is most widely kind of known. So controlled NOT gate takes how many inputs? That is the first thing. It takes into consideration 3 inputs, right? So where, say I'm writing it in this way, control 1, control 2, and target. This is your input configuration. And your output will also look like that, C1, C2, and target. So initially, with 3 bit, how many configurations are possible? 2 to the power of 3, right? So let me write it down. So it's 0, 0, 0. Any way you want, you can write. So it's a 0, 0, 1, 1, followed by 0, 0, 1, 1, and 0, 1, 0, 1, 0, 1, and 0. So it works in this way that whenever the logic is very simple, if and only if both the controls are 1, then only you have to flip the target. Otherwise, you need not to do anything. So very simple one. Only if both are 1. So it is something like that. If I have to write it in the propositional logic format, so if C1 and C2 both are AND, then only you have to say flip your target. Something like that, right? So that means in all the first 6 configurations, we don't need to do anything because both the values are 1. This condition is not present. So it will be exactly same. You can write it down. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Now, if you check this part, it's 1, 1, 1, and 1, 1, 0. So only in this part, you can see that if your target was 0, right now it's 1. And if your target is 1, right now it has become 0. Right? So this is kind of the truth table representation of this thing. So whenever both the values are 1, then only you will be flipping the target. This is called a Toffoli gate. And how in Qiskit it looks like? It looks something like this. Since you have both control, I have told you that field bubbles are representation of control. So these two are control, and this one is your target. This is a C1, this is C2, and this one is your target, T. Okay. So from here, if I just write, say I have done something like this. Repeat C2. C2 not. C2 not getting your question, maybe. I hope you are asking this circuit. So this means the two field bubbles are representation of control. I just have told that you have to only flip if both the inputs are 1. So you check it only in these two cases. Sorry. Just a minute. So only in these two cases, you are getting your 110 and 111. The cases where both C1 and C2 both are 1. Right? C1, C2 means qubit. All of them are qubit. C1, C2, T. All of them are qubit. Instead of just writing it Q0, Q1, and Q2, I am just writing it as, or maybe need as C1, C2, and T. They are nothing but Q0, Q1, and Q2. Let me write it down. Say, so Q0, Q1 is this, and Q2 is this one. So now, here I am doing this, and then here it is kind of this. Then say an X gate till this part, I think I have covered. Then so this is an arbitrary. Arbitrarily I have taken. What are the logic gates that I have used over here? Quantum logic gates, Hadamard. This is Hadamard. This is CNOT. This is Toffoli. This is a NOT gate, X. This is another CNOT. This is another CNOT. And what is Q0, Q1, Q2? 3 qubits. So it's a 3 qubit system, right? If I have to just write it down, that what are the operations or what are the quantum operators that is working on which qubit? That kind of mapping, if I want to just write it down, I'm just writing it in this way since I do not have that much space here. Just follow that. So first one is I'm applying an Hadamard on Q0. Done. Second operation is I'm introducing another, I'm just not writing the Q1, Q2 initialization part. So of course, initially you have to initialize Q0, Q1, and Q2. So I'm considering that all of them are already initialized with gate 0. So now what I'm doing is I'm applying a CNOT where what is my control? Q1 is my control. How to identify that? You have to identify from the circuit where you will be getting the field circle. So here it is present. So that means Q1 here is your control, and the XOR kind of symbol or plus kind of symbol you are getting here. So this is your target. So it's a CNOT Q1, Q0. And of course, the sequence here in the quantum gate or in the quantum programming representation, this is the QASM, quantum assembly level representation, it of course matters. Why? Because it represents that which is your control and which is your target. Okay? And all because of all the controlled kind of gates, the ordering is very important. This is the second operation. What is the third operation? You are again doing another Hadamard on Q2. Okay. What is the fourth operation? This is a CCnot or C-square not a Toffoli, which are control Q0 and Q1, and Q2 is target. So that means it's a CCnot Q0, Q1, and Q2. In some programming language, this CCnot can be represented even maybe directly fully or in some other form. That is just the naming. You have to follow that particular format. But this is the basic one. This kind of a quantum programming principles, you can say. Language-wise, it will differ. I'm not here writing the, I got your point, Akash. I got your point, Akash. Yes, okay, two things. First, I'm not drawing the timeline kind of time diagram. Why? Because I'm not going to again explain it. A quantum circuit was not under the scope for QT-02. It maybe will be present somewhere later. And here, since we are not covering quantum algorithm, otherwise it will take a lot of time. If time permits, I will be maybe doing it. If time permits, or whenever we will doing the teleportation and dense coding, this kind of quantum circuits will be there. There I will explain in terms of the time diagram. Understanding that explanation, you can randomly create a circuit and try. You can do your trial accordingly. Okay. So fourth one is. This was the first question. And second question, I have seen one that few operations can they interchangeably be used? Absolutely. Absolutely. There is no issue in changing a few of the ordering of the instructions only if there is no dependency. So that kind of a dependency that we have seen, that there should not be any structural dependency, data dependency, control dependency. Just do a check here as well for the data and control. If you see that you can do that, then it's okay. Say head about Q0, head about Q1, head about Q2. Can they interchangeably used? Definitely. If it is head about Q0, then CNOT Q0, Q1. Can it be interchangeably used? No. Why? Because your head about is in next line someone's control. If you first do it control, then you apply head about, then that will not make any sense. So likewise, you have to understand that which quantum instructions are dependent and which are independent set of instructions. That's a part of quantum compilation and all those stuff. Again, okay. So fifth one is the NOT gate. On which qubit I'm doing it? I'm applying it on qubit 1. So it's a NOT on qubit 1. Obviously, just see the ordering thing. The NOT of qubit 1 is an operation. But what if I do it first? Then the meaning will change. Because why? Because before that, with the initialization value K0, I am supposed to put it as a control on some other qubit. But if later initially I apply the NOT gate and I make it 1, then the control will be 1. So that will do a trigger, which is not the desired output that I should be doing. Likewise, please do your analysis. So it's a NOT from Q1. I'm done with that. Then remaining are two operations, 6 and 7. So 6 is Q2 is control and Q2 is control and Q1 is target. So CNOT Q2, Q1. And last one is another CNOT Q1, Q2. These are all the 7 set of operations. Right. Accordingly, you know new quantum gates, you just apply it. Better thing is to draw the time diagram, and if you want to do then convert into the matrix form, then check that what is the output that you are getting, or whether your quantum state evolution that is correctly happening or not. Okay. Then, so CNOT, C2 NOT we have seen. Next one is a swap gate. So in swap gate, what you do, you just make the content, you just interchange it, just like we do in our classical thing. It's the same thing. If your Q0 right now has initialized with K0, and if your Q1 has initial right now value K1, swap means swap of Q0, Q1 means you will now interchange the value. So you will put it over here and you will put it here. That is a swap gate. Okay. And it is like this in the quantum circuit form. Okay. Okay. Now there is a phase gate. Phase gate. Phase gate is this kind of thing, Z. So it's 1, 0, 0 and e to the power I theta This is the general form of representation. But particularly for phase, we write 1, 0, 0, minus 1, right? What's called a phase? If you put it on 1, 0, it will keep it 1 into 1 plus 0 into 0, that is 1, and 0 into 1 plus minus 1 into 0, that is 0. So it will change, nothing it will happen. So it will keep it as it is, Kate 0. But if you just put it on Kate 1, which is 0 and 1, then it will become 1 into 0, this is 0, but 0 into 0 plus minus 1 into 1, that is minus 1. So it's a minus of Kate 1, where it is a, initially it was a class Kate 0. So that means it just changes the phase from 1 to minus 1, and 0, it does nothing. 0 plus 0 and minus 0 does not really make any sense, so it does nothing to that. Okay. But general form is this one. Now, if I just put here, first of all, what is this thing? If you are well aware of Euler theorem, so it's nothing but cos theta plus I into sine theta. Now, of course, you understand that if you just change the theta, accordingly, you are going to get any type of quantum gate that you can desire for. If you put there theta is equals to pi, you will be getting something. Theta equals to pi by 2 will give you something. Likewise, it is called fifth gate, S, T, all those gates. So Z, S, and T are almost kind of originated from the same thing, just by changing the value of theta. So if I just put here 0 and e to the power I pi, then it will be cos pi plus I sine pi. So this one is what? Cos pi. This will give you minus 1, and this one is 0, so ith component will not be there. Theta equals to pi, absolutely. So that means e to the power I pi is nothing but minus 1. So if I just put it over here, so it will become 1, 0, 0, and minus 1. This is Z gate. Yes, this is your Z gate. There are a few gates, single qubit gate known as sigma X. Sigma X is nothing but the NOT gate, and Z already have said. There is another gate known as sigma Y, or say Y gate or sigma Y, we often call it. Now, if you want to get that one, so I just want to write it down. These are called Pauli's gates, okay, or Pauli matrices, sigma Y and sigma Z. So sigma Z and Z, that is equivalent. Sigma X and NOT, that this is equivalent. Let me write it here. You represent in this way. Z is nothing but control, this 1, 0, 0, minus 1. Only I want to give you the sigma Y, which is nothing but 0, minus I, and 0. Okay. So it generally gives it in the complex space or imaginary space. So if you just, I multiply I with the sigma Y, just do it, then you will be getting 0. This is I into minus I, that is minus I square. Y square is minus 1. So minus minus will get cancelled out and will be giving you only 1. Then this one will be I into minus I. Sorry, I into I, that is I square, that is minus 1. And this one will be 0. So in order to get it in the real plane, you need to really multiply the Pauli Y with an imaginary amplitude I. This is Pauli's matrices, this is swap, this is phase. And that was Toffoli, CNOT, and Hadamard. And all the S, T, Z, they all originate from the same thing. You put pi by 2, I guess that is something, S or T. You have to check it. Okay. There is another concept which is very important, which is C phase. C phase, how it looks like. So it's exactly kind of the sibling of controlled NOT, CNOT. Just there it was this thing. This was for CNOT, where this is the control. Accordingly, you just change that or flip that bit, right? This was CNOT. C phase is control will be there as it is, no issue. Target will be here like this. So it's a Z, but Z itself will be applied only if there the control is not. That is it. Okay. That was the thing. Now, I think let me just cover Hermitian. I'm done with the quantum gates, as you will require it. But this much of a detail maybe not required for your quiz, but just for the sake of a completion or kind of a full feeling, I'm just telling you. One more thing is remaining, that is the Hermitian operator. That was there. So the reference for Hermitian comes from that place where we actually Copenhagen interpretation and quantum mechanical postulates. So, and linearity of operator, we actually had done till this part. I guess it is covered in lecture 2, if I'm not wrong. So just take the lecture 2 part, and here one part was missing. So that is called Hermitian. It covered on the same day. I thought to cover it when we covered the orthogonal and orthonormal, all those things. So Hermitian operator. So for coming to Hermitian operator, let us start with the adjoint of an operator. Okay, let us start with that. So adjoint of an operator. Measurement of this. Hold on your interest. Okay, adjoint of an operator. So suppose I take the inner product versus scalar product of inner product is scalar product. I hope right now this picture should be very clear in your space. Inner product means the that particular thing where it's within two curly braces. Okay, a curly angle there is something. I hope that picture should be clear. So scalar product of this phi with the vector psi. That means, say, this thing and a times this psi. So if I'm able to write it in this way, where this is called a dagger, this particular symbol. So it looks like this kind of like that. Okay, this is called a dagger. Okay, then if a dagger of dagger is equals to a, then we call it a self-adjoint operator. Okay, this dagger is almost equivalent to the transpose thing. The difference is here it is in the imaginary plane, for it covers a complex space, and there it is only covering the real numbers, where we are getting the A transpose of transpose, that kind of thing. So it's kind of similar thing in the complex space. Okay. Now, with example, you will understand it. Just wait. So, the dual of secant, this thing, A psi, is nothing but in the bracket form. If it is a dual of ket, it is a bracket form of this thing, a dagger. This is dual. So this is nothing but its dual is a dagger. If you remember also, we were mentioning that if it is only 0, then maybe you are getting it in the whenever you were converting the row to column to row. I told you that just put a star, or you have to put a dagger, because if it is I, then you have to put a minus I. If it is 5, you can put it directly 5. Okay, there was a reference. While I was talking about the direct notation and duality, or kind of a bracket notation where Kate is the dual of bra and bra is the dual of Kate notation, how to write it, how to do the representation, all those stuff. Okay, so but right now, since it is in the complex space, definitely, so I am using perfectly the dagger symbol. It's not actually multiplication, it's just the operator form. They are not really complete, so they have to be completed. But it is the way we write the, say, bracket Kate is nothing but some operator kind of stuff. Okay, bra itself, it is a notation. It's a direct notation. Of course, it itself will not work. It has to be applied on something. Okay, so it's not multiplication directly, it's just the representation, but it's not yet complete. Okay. So if I put it, I'm giving the explanation here. Just check it. So phi, this thing, so that is a dagger of this. I can write it down in this way. Then psi, a dagger phi can be written as this a dagger times dagger phi and your Kate psi. Where this is nothing but a, phi and psi. Considering your a dagger of dagger is nothing but. Okay. If some of you are still confused with all the symbols, with example it will be easy. But before that, it's very easy one. So first, let me just write the definition for self-adjoint operators and why it's very important. So first of all, self-adjoint operators are one class of operators which is going to be extremely important with reference of quantum mechanics discussion, because these operators can represent physical observables. And they are also known as Hermitian operators. So Hermitian operators are nothing but self-adjoint operators. Okay, so why they are very important? Because they can represent physical observables. Yes. In quantum mechanics context. And they are also known as Hermitian. And Hermitian operator definitely has a property of self-adjoincy, which is a dagger of dagger is equals to a. Okay. Or a, sorry. That is a dagger is equals to a. Just like A transpose and A, they are similar, they are same. Here also it's a dagger is equals to a. Now, by saying that an operator acting on a vector space, say now, an operator acting on a vector space wait करजो gives, you will be yourself able to answer it. Just a minute. An operator acting on a vector space gives another operator in the same space. Then a general same space, this space means I'm referring Hilbert space. Then a general representation. Therefore, a general representation, not audible. Am I not audible? Okay. A general representation of an operator looks like, or could be in quantum, this thing. This is an operator symbol. This is a generic symbol of an operator, a theoretical definition of an operator in quantum mechanics. So it looks like this, which is a kate followed by a round notation. So if you also see, kate is nothing but a column vector form. It's a column form. Bra is nothing but a row vector form. So say column means it's a like n row and one column. N row and one column, and it is one row and say n column. N column. Then if you multiply, what it will be? It will be an n cross n matrix. Absolutely. So it is the outer product form. And this also is known as matrix direct form. So just like this inner product form looks like this, anything kind of that. So outer product or matrix direct form. And this is a bra followed by a trade. And here it's a kate followed by a. So it's a kate bra. This is always giving you a scalar, but ultimately this will give you a vector form or a matrix. Okay. Now, the example that I was talking about. Say A is a matrix. It's 1 plus 2i minus 5i, 3i, and 4. There is nothing from quantum here. It's purely a part of linear algebra, this Hermitian. But only the quantum operators, they follow the properties of Hermitian because they're self-adjoint, all the properties hold here. Just like orthonormal, it's a property of linear algebra itself. But orthonormal vectors we need in kind of quantum. Similarly, at self-adjoint properties or these operators we need. Okay. So how to do that? First step is you have to take a transpose. Transpose of it. Transpose means all of you know row to column, column to row. And second one is then take a complex conjugate. Right? So that means your A dagger will look like what? First it is a transpose. That means here it will be minus. Okay, let me write A transpose first. So it's minus 5i, 3i, 1 plus 2i, and 4. Right? After that, you have to apply the complex conjugate. Anything to write it or A dagger directly, it will be what? 1 plus 2i. What is complex conjugate of that one? 1 minus 2i. 3i, it's minus 3i. Minus 5i is 5i itself. And 4, it's 4i. Just write it down. So it's 1 minus 2i, then minus 3i, then 5i, and 4. Now, according to the example that I have taken, just check whether A is equals to A transpose A dagger or not. The answer is no. These two are different matrices. Right? Therefore, A matrix is not a Hermitian matrix. It is not Hermitian. In your quiz, we will be getting questions from properties of Hermitian and the logic that you have to derive from it. So directly no matrix will be given to you. I have to check that whether that is Hermitian or not. That is very easy, but we have to know the interpretation in quantum for Hermitian. So everything that you will be watching or maybe getting in the quiz part, at least for my part, because I'm covering mostly the theory parts. So it will be a concept followed by its interpretation or applicability in your quantum. No, 4 is only 4. 4 is not minus 4. 4 is just a real number, so it's only 4. Quiz will be MCQ and 5 questions will be multiple select type. I explained it during the beginning of today's session. Okay, now just one more example just to show you A is not Hermitian. Yes, that is the conclusion that this matrix is not Hermitian. Now, if I just take another matrix, say B is another matrix that I'm taking. I'll not do any derivation, you will directly check it. It's a Hermitian. So it's 2 plus I, 0, 1 minus I, say. And here it will be then 3I, 1 plus I, and 0. Okay, great. So it's just to calculate B dagger. B dagger. So row and column, all of just first put the transpose, change it. So your 2 minus I will now come here. Minus 3I will come here. 3I will go here. So it's a A11 to all these things, right? A11 will be 1, 1. A12 will now go to A21. Then you have to do the complex conjugate. So after putting 2 minus I here, if you then put the complex conjugate on 2 minus I, it will be again 2 plus I. So that is a Hermitian matrix. So it will be exactly same as B. Therefore, to get that, then B is a self-adjoint or a Hermitian matrix. Okay. Now, without any further delay, let me start first no cloning theorem. I don't know what's the time now. Check it. Can anyone put it? Again, I have to do all this. It's 2:50. Thank you. Just as a problem. It's 2:50. So, thank you. So now we will be covering 3 things. No cloning, quantum teleportation, and super dense coding. And the priority itself is in this order itself. Already I have given quiz questions, so I have to cover. That is the first thing. Second is, now before starting no cloning and quantum teleportation, I want to give you a proper flow. Why we are doing it in this way? Because no cloning and quantum teleportation both are fundamental aspects of quantum cryptography, which we will be covering in QT-02. So these are those 2 important postulates that we have to do. We cannot ignore if we have to understand quantum cryptography. And in quantum cryptography itself, it has a maximum application. No other else. And teleportation has some application in communication and networking as well. Quantum communication and quantum networking. Super dense coding is just the kind of a reverse process of quantum teleportation. So I thought of including this process itself or also into our course curriculum. But teleportation is a must and no cloning. First. Second is, in order to understand all these 3 concepts, at least the teleportation and super dense coding, we need to understand the quantum circuit form. Otherwise, we cannot understand that. And in order to understand quantum circuit, we need to understand those quantum gates, which we covered in our last class and in today's class. That is why the structure I have designed it in this way, so that all the basic modules or fundamental components are covered. Okay, with that note, we have to remember now everything. And while describing the teleportation and all the stuff, I will be doing in the time diagram as well, so that it's kind of fully covered. Okay, so let me start. So first, I want to give you a story. I had given it in the lecture 1 for QT-02, where what is no cloning theorem first? So no cloning theorem is a property of quantum mechanics that prohibits you or any user to recreate or clone or copy a particular quantum state. What do I mean by that? If I have some quantum state that is an arbitrary quantum state, I also told you that except to few very trivial exceptions, this is the same for all. So no cloning property of quanta works for any of your non-trivial cases, which are arbitrary cases, right? So in other words, if you think it of a Xerox machine, say the cloning operator is equivalent. I'm not writing anything, I'm just explaining. So say cloning operator is nothing but an analog of a Xerox machine that you see. So the logic is, even if you derive some logic, if you give, say, a math paper through the Xerox machine, and if it is able to clone all the 2 pages of the math paper, then your machine should also be able to, if you just give an image, or if you just give another, say, research paper or anything, any else paper, original paper, it should also be able to clone that. That is not possible. Even if for one particular case, anyhow, you figure out that how to clone that one, that operator or that unitary operator is not universal, that you cannot say that it works for all cases. So that's why we say that no cloning or the quantum cloning, state cloning, is never possible. Okay, so say, I'm just writing it now. Say no cloning. Say I have a blank state. I have a blank quantum state. What I want to clone? I do not want to clone a paper here. I want to clone a quantum state. Okay. So a blank state looks like this, K0. And there is an original, say, paper or math paper. Bhagya Lakshmi, I think there is no issue from my end. Please, you just rejoin. Thank you. So there is a blank state. It's kind of a blank paper that we insert into a Xerox machine and say, my original quantum state is psi. So I want to copy this one onto this one, right? So say, considering my no cloning operator or unitary operator U exists, okay, considering that, if it exists, then I should be able to clone it. So I should be able to copy this thing into this. So my blank will now become this one. This is after copying, okay, and this was your original. So it is a cloned copy, a clone version. And this was your original paper. Or definitely original paper also comes out. So this is the thing if no cloning operator exists. Now say, what is our claim for no cloning? Our claim is there does not exist any unitary operator U such that this particular function, say f, holds. Right? I can write it down in this way. So suppose this exists. If anyone is not understanding this, this is a there exist operator. This means such that, okay, and f is the function. I'm writing it in this way. So suppose this exists, then we prove it by reductio ad absurdum. That is, we will assume it holds, but then we'll see it does not hold, nothing else. That if it were possible that such U exists, such U, what is U? Unitary operator or cloning operator exists, then it should be able to also clone some other state. This thing should also be possible. Right? Now, if this is true, considering this is also true, Therefore, the inner product of psi and phi, that will be, just see how I'm doing it. I'm introducing few identity operators, but that identity is not like the way we introduce in classical. Okay, it's in a quantum realm. So I'm introducing what? I'm introducing a inner product form of 0 and 0. Can I do that? Yes. Why? Because 0 and 0 inner product gives me the scalar value 1. Of course, that is allowed. Right? So this thing times phi is as it is. So I'm just introducing this new thing. Write the logic here because this is nothing but 1. Why 1 and all? You should now be knowing it. Nothing I'm writing that you will not be finding anywhere that there is no logic or randomly I'm writing. Okay, everything is a proof. If I'm not explaining it here, that means I have already explained it. Okay, this is the inner product form of phi and psi and phi. And what I'm trying, say, what is my ultimate agenda? I'm trying to disprove that cloning exists. So in order to do that, I'm doing a few mathematical steps so that ultimately it comes out, or I reach in a particular situation where it can happen only for some triviality. I can prove that. Right? That is something that I want to introduce. Just like, say, in our kind of discrete mathematics or in terms of abstract algebra, we add those things, right? That if we want to get 1, we add 0 plus, say, 0 bar, something like that, or a plus a bar in Boolean algebra. So just like that, here I am adding inner product form of 0 and 0. That is 1. Those who are attending today itself, this is your first class. It should not be, but still, considering that, this is 1, 0, and this one is 1, 0. Just multiply 1 into 1 plus 0 into 0. That is 1. Since outcome is 1, we are introducing it. So this is called an inner product form. Also a quick thing. This is nothing but 1, 0 into 0, 1. Multiply them, 1 into 0 plus 0 into 1. This is 0. So the inner product of the two similar states is only 1. Except otherwise it is 0. Right? Considering that. Let me again come back. Where I went initially, so it was this thing. I hope right now for those who are having some issue in understanding that why I'm introducing it, that is not there anymore. Just a minute. Yeah. Please follow the steps. Follow the steps. So I can write it in this way. Now see, I'm mapping 0 with this thing and I'm taking 0 with 5. And I'm introducing another operator. What operator? U dagger U. What is dagger? Right now you should be able to know. Right? And definitely the one who are asking some inverse related stuff. So just like U into U inverse is 1. Right? So it's an identity operator. Absolutely. So this is an identity, nothing else. And this is dagger. So U dagger U, I'm again introducing, just like I introduced initially 0, 0 scalar product or say inner product form. Again, I'm introducing. So this is nothing but phi and 0. Phi 0 will be as it is. Okay. Now, this means, and why I'm taking, again, let me write it down. So U dagger U is nothing but your identity. Dagger. So this is psi. This one is also psi. And this is phi times phi. From where I'm getting it? U with this thing. From the definition itself. Why? Because from the definition of function that I have taken here, considering this is true and also considering this one to be true. So this is 1 and this is 2. This phi 1 is 2 and psi 1 is 1. Nothing else. So if that exists, then of course I can write it down. But if I can write it down in this way, that means that it is nothing but psi phi, this thing, whole square. So initially I started with the inner product of k psi phi. Right now I'm getting k psi and phi this thing whole square. If I am reaching in this particular condition, what can I infer from this? I can infer that either my two states are orthogonal or two states are identical, right? Why? Because if orthogonal, that means both sides will be zero, nothing else. For orthogonal matrix, we have seen that inner product of two things, that is zero, right? And for identical, yes, if it is identical, then it will be 1. That means either phi and psi, they are orthogonal to each other, or phi and psi both are the same state. They are not different states. So that means that either the two states are orthogonal. Those who are new in today's class, orthogonal property, just do a check. Okay. You should be understanding everything. That is what my motto is. Or the two states means your psi and phi. They are identical. Either they are orthogonal or they are identical. So if orthogonal, then this thing and this square is 0 for both sides. And if identical, that is 1. Okay. Therefore, this and this cannot be any arbitrary states. So our assumption, considering if u or the cloning operator exists for psi, it will definitely exist for phi, and it can clone phi as well. That condition or that claim was false. Okay. So looking for an operator that can clone any arbitrary state is not fulfilled. So quantum cloning does not exist. Does not exist. And this principle is called quantum no cloning theorem. Okay. Everything clear till this part? Yes, thank you. One has mentioned that explain again. What again you want me to again mention? The entire no cloning theorem? That is not really possible. Any part, if you're having any doubt, please ask that. Entire thing is not possible. All the other states, yes. That means if you have to clone something, then only the identical state, that means it's the same state itself and the orthogonal state. So the basically quantum cloning can work. It can clone a particular state only if that particular state is orthogonal. You can recreate it. Clone means you can ultimately recreate some orthogonal states. But in quantum, it's very random, and the property itself will ultimately decoher, and it will be again some probabilistic value. So that you cannot do. That is a claim. What if you could do that? If you could do that, or if quantum cloning exists, then what will happen is ultimately, if some eavesdropper, that is application. So if some eavesdropper is actually able to get your quantum state, which is an arbitrary state, you definitely will not encode a very simple state. It will be some percent of something, some percent of something like that. So that particular quantum state, if eavesdropper is able to get that, he is not able to clone that. Or if he tries to clone that, then what will happen? What will happen is it will lose the quantum property. Because ultimately, if you anyway try to measure a quantum state, which is holding some probabilistic nature, whenever you are trying to poke that particular state, it will lose its quantumness. And ultimately, post that, on measurement, you will be getting the value. But after that, you can never again recreate it. So the intended receiver, on the receiver end, once we'll be getting your distorted value or your touched value, or say popped value, from that value itself, he can or she can easily understand that there is an Eve or an eavesdropper in between. So that particular communication needs to be discarded. We call this kind of an attack of a man in the middle attack, MITM, and this particular attack is not possible with quantum communication or quantum cryptography, right? Great. Now I will be, thank you. Now I will try to cover at least that part, quantum teleportation. No interruption. Do your full focus. Ask very relevant questions and in context questions. Post that, I will be giving all of you time. Quantum teleportation. So from the word teleportation, you can understand it's ultimately the process of sending something to somewhere. That is kind of teleportation. But the thing is, what is quantum teleportation? What you want to teleport here is a quantum state. So this is the process of sending one quantum state from one place to another. Right? For that, now we will look into it. Either it's the sending of a quantum state or it's something else. But that is our agenda. That is our goal. Now we will slowly getting into the procedure for that. Say Alice and Bob and Eve. These are the three terms. It initiates from this teleportation and it will follow in all the cryptography and communication phase. And in also general, I think networking also, we follow this thing, cryptography, Alice and Bob. So similarly here also we will be following the convention that Alice is a sender and it's a she. Alice is a female character, Bob is a male character. So, and Bob is the receiver. And we want to do some communication from Alice's end to Bob's side. That is kind of a common convention. Okay. So Alice has this thing, say alpha times K0 plus beta times K1. And this is the state which, and this state, Alice wants to send to Bob. Right? Considering that Alice also, considering this is an arbitrary state, that means that Alice has no precise information on alpha and beta, what it is. Otherwise, she can just call Bob and tell that alpha and beta are the coefficients, please you recreate it. That is not possible, considering that. Okay. Now the catch is when earlier Alice and Bob met, they decided to do one thing. That is, they decided beforehand to share one qubit from an entangled Bell state. Okay, so Bell state is nothing but this thing. We have seen this Bell state. Okay, this is one of the Bell states. So earlier, there is a story, of course. There is a story. So earlier, when Alice and Bob met, they decided to share one qubit each. One qubit each from a Bell pair, which is an entangled Bell pair. And if you remember here, entangled Bell pair means definitely there are two qubits. Only one qubit cannot be entangled. Self-entanglement is not possible. So of course that means there are two qubits where one qubit Alice will be taking, one qubit Bob will be considering, sharing. So only this thing is common between both of them. And Bell state is common, like any of the Bell states we can use, but here we are using K00 plus K11 by root 3, where this is qubit 1, and this is qubit 2, and this is qubit 1. Okay, I'm not writing qubit 2. so that you understand that in a base state itself, that I want to refer this, that this qubit is qubit 1, this is qubit 1. So qubit 1 will be having, say, under control of Alice. So let me write it. Say Alice will be having a control on, I will assign qubit 1 to Alice, and I will assign qubit 2 to Bob. Okay. So ultimately, how many states are there? So initially there is a state 1 is nothing but the state that I want to share, which is alpha ket0 plus beta ket1. Now I have an entangled pair like this, where this one and this one will be referred as bit 2, right? And this one and this thing will be referred as bit 3. And Bob will have access to this one, and Alice will be having access to bit 2. Bit and qubit, if you want, you can also write qubit. Okay, so this is the configuration. This is the configuration. Now, let me show you that how the quantum circuit looks like. First, let me draw the circuit. So, I will explain with the time diagram and everything. And also the measurement. When we're asking question on measurement. You should be now knowing that this is a measurement symbol. This is Hadamard, this is CNOT. So this is your alpha. Say qubit 1, qubit 2. Qubit 1 itself is a entangled, a superposed qubit, which is alpha ket0 plus beta ket1. This is your, and this 2 and 3, they like qubit 2 and qubit 3, this is a part of your base state. Right? This is the thing. Where from here, the output that I'm getting, I'll be applying a X gate. What is X? So NOT gate or Pauli X. Right? And from here, whatever you are getting, you post that, you will be putting a Z gate. What is a Z gate? It's a Pauli Z or a simple phase gate. Now, what is the claim? That if you have started with, say, gate psi here, which was your alpha 0 plus beta 1, here you should be getting, because this is bit 3 is associated to Bob. So you have to assume that Bob is here. So on these two, Alice have some control. 2 and 3 is a entangled base state where both Alice and Bob has control. But 3 is the only one where Alice does not have any control and it is under control of Bob. So your target is that gate psi should ultimately be able to be found at Bob Z. After this entire, that should be your target. Okay, now this part is Alice's encoding. Alice has done bit 1 and bit 2. Bob has no control on that. So this is Alice's encoding. There is a classical communication channel, which is this thing. So another point to be considered here over here is teleportation needs some classical channel, but it transfers what? It ultimately transfers a quantum state, but it also takes help of some classical channel. Okay, so this is the circuit. Now, say, follow the circuit. You should be having the circuit with you. Okay. So Hadamard on first qubit, what I'm doing? Hadamard on first qubit. First I'm doing a CNOT, followed by a Hadamard on the first qubit and measurement of first and second qubit. That is what I'm doing. That is Alice's to do, right? Okay. And this part is what? This part is just to create the, this is nothing but to create the entanglement. Entangled belt pair. Okay. Therefore, Hadamard on first qubit and measurement on both first and second qubit are Alice's 2-bit cell. Okay. Now let me write the entire quantum state exactly at this point. Where what I'll be writing? I'll be writing this particular state. Okay. Followed by that, I will be also writing the entangled Bell state, which is QT-00 plus 1 by √2. And there is an alpha beta associated with psi as well. So after a bit of rewriting, I'm writing it, then I will be applying the operations. So therefore, it's nothing but alpha by √2. I'm doing on all the states. I'm together writing the equation. So it's a QT-0 and why I'm writing in this way? Because I want to apply the quantum operations, nothing else. Plus beta by √2 QT1 times QT-00 plus 1. Okay. This is the entangled one, entangled Bell state. Similarly, this is entangled Bell state. It is coming from qubit 2 and qubit 3, and this is a part of qubit 1. √2 by √2 is 1 by √2 is coming from the entangled Bell state, and alpha and beta are coming from the pure side. That was the thing. Okay. Now separately, now what I want to do? I want to apply a CNOT, which is a part of qubit 1 and qubit 2. So likewise, I will do a bit of change in the configuration. My target is so that I can see the effect of the applying the quantum gates very easily. So that is my target. So now separately extracting out Alice's part. Alice's part means qubit 1 and 2 part. Equivalently, we can write it down, this thing. That is 1 by √2, say, alpha, I'm again entering into here, this 0, 0 and 0 plus alpha 0, 1 and 1 separately. Okay. Since I've taken 1 by √2 as common, so beta again will enter here and I'll be doing 1, 0, 0 plus beta 1, 1, 1. I hope it is clear to all. Just a rewriting. Okay. Now I'm applying what? I'm applying CNOT. CNOT means a control knot. So one is control, another one is target. So that means this is control, target, control and target. It's a control, this is your target. This is your control, sorry, this is your control and this one is your target. Let me write it down now. But it will happen alpha 0, 0, 0, nothing will happen, plus alpha, this is 0, 1, 1, plus beta 1, 1, 0, plus beta 1, 0, 1. So it's 1 by √2 times alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 1, 0 plus beta 1, 0, 1. In previous line, it was 0, 0 plus 1, 1. Where it was? Which previous line you're referring? I guess the, oh, yes, I guess the first line. Now separately, yeah. Nothing is changed. I'm just 1 and 2, 3 was together. I'm just putting 1, 2 together, keeping 3 outside. This is in the first line, this line. Then I'm applying a CNOT. Okay? That is it. Okay. After that, again, let me go back to the circuit now. So in time diagram, I am right now in this part. Say this is T1. Now I will be applying Hadamard, say T2. So after T1, I am here. So this is after T1. Okay. Now what is the next step? On this outcome of T1, I have to apply a Hadamard on what which qubit position? Not on all. Only on the first qubit position. So first qubit will now be Hadamard, right? So in first qubit position, you can either see a 0 and a 1. So now you should be knowing that what Hadamard does on kit 0 and kit 1. Okay. I'll not be writing it. So or say this much only. Say this is kit 0 plus kit 1 by root 2. Since and Hadamard on kit 1 will nothing but be kit 0 minus kit 1 by root 2. So equivalently, we can write from the earlier one, alpha, it was kit 0. So this kit 0 will now become kit 0 plus kit 1 by root 2. And this 0 and 0 will be as it is. Okay. So accordingly, I'll be putting only the Hadamard output on the first qubit position out of the 3 qubits. So this thing, kit 0 plus alpha, kit 0 plus kit 1 by root 2, kit 1 plus beta, kit 0 minus kit 1 by root 2, because I had 1 here, kit 1 0 plus beta, kit 0 minus kit 1 by root 2 times kit 0 and 1. Now 1 by root 2, everywhere I can put it outside. So it will be nothing but half 1 by root 2, and here also 1 by root 2 will come. So it's half. And then this 0 and this 0, I'll be writing it this way. Okay. So now, can I just write it down? This 0, 0 and alpha kit 0. Just see whether I can write it down or not, or the equivalence holds or not. Plus this thing 0, 1, alpha 1 plus beta 0 plus 1, 0, alpha 0 minus beta 1. Why I am writing in this form? Again, just after some steps you will understand. Plus 1, 1 and alpha 1 minus beta 0. There is nothing quantum here. Only some simple maths. Okay? I'm just rewriting it. And here you have to rewrite, otherwise you will, maybe in some cases you will not be able to visualize how to measure it. So for that only I'm writing it in this way. Now whenever Alice makes a measurement, she can get either 0, 0. Just see it over here. Now what is my target? Alice has to make measurement, right? Of which qubit? Qubit 1 and qubit 2. Here you can see that. So qubit 1 and qubit 2. That is why I have taken them out so that I can understand what is the measurement. After that, if you also notice one more thing, that after measurement, I am using some sort of classical channel in order to send these two, this line and this line's information to Bob. After that, Bob is doing something. That's a different thing. On third qubit, you can see this is third qubit. Bob is doing something, but first I am measuring first 1 and 2. Whatever I'm getting, I'm just putting them both on a classical channel and sending that classical information through a classical channel to Bob. Clear? The circuit equivalence and the logic and the maths here. I hope you are able to map now how it works, at least in first level. Okay. So now this is what I am getting. So first two in thing I have separately taken them. Third one I have kept. So now everything will go in a differently. Now from the circuit itself, now you know that Bob has an access to this one. Bob has an access to this. Bob can get this or this. What it can get, I do not. But Bob on measurement can get any of these things. That is the theory of measurement. And I can get any of the output. I have not done any step, but what I have told you here is from this thing to this thing, why I have written it in this way. You might be asking this question, right? That why suddenly we need this kind of reordering. For that, I told that for this, you have to, if you have to understand it, you have to refer and go back to the circuit itself for teleportation. If you see the circuit where right now I am in the Hadamard state. After that, I've done some sort of change of my equation. Why? Because I want to measure quantum qubit 1 and qubit 2. So I have put separately qubit 1 and qubit 2 accordingly, and third one I have kept separately, because third one is the only one where Bob solely, dedicatedly has some access. Alice has no input on the third qubit. Accordingly, only we are encoding from the very beginning. So that is the only thing that we can do. So if I just put here, say another time diagram, say T3, now let me write it down that after I got this, okay, so after T3, what can happen? Whenever Alice makes a measurement means this thing, okay? Measurement, she can get either 0, 0, or 0, 1, or 1, 0, or 1, 1. Any of this. Now, depending on what Alice gets, Alice will pick up a classical channel like a telephone or something, and Alice will now be sending the information that, okay, I have got this. Right? So Alice can send either 0, 0, or 0, 1, or 1, 0, or 1, 1, depending on what kind of 2-bit value Alice has got. And Bob also can receive any of these things. Now, there is a beautiful thing if you notice. Let me again just write this part. So initially it was 0, 0 when these two were the first and second position. Third position, which Bob has only dedicated access, is the original state. This is the third one. But see, this is the original state. Nothing has already, nothing else is there. So, and now, third state, eventually, one way or the other, by through some our quantum operations, or through the circuit, through the time evolution, ultimately is already there with Bob. So that means if Bob receives alpha 0 plus beta 1, then definitely how Bob will understand that whether she or he has received the correct one or not is through Alice's those two sent bits. Now, if Alice sends 0, 0, it's a clear signal to Bob that, Bob, please don't do anything. So Bob will apply further operations, as you can see, like X and Z gates, only depending on the inputs coming from Alice's end. Okay? Have you understood the logic? Now, rest part is simple maths. Please give a thumbs up or something if you have understood this part. Thank you. I got, okay. Thank you. Thank you. Now see how Bob will interpret it. Okay. So, if say now say, focus. Say Alice has got 0, 0. So Bob will do what? Bob will not do anything. Bob will do nothing. And because alpha 0 and beta 1 has been successfully not sent, rather it has been successfully teleported. Sorry. Wait a second. I can translate. It has been teleported, or the correct word, more appropriate word should be it has been recreated. So it's not really the physically sending some data in quantum like we do in classical. It's a recreation of that particular state. Now this is case 1. Bob is not sending any bits here. Bob is just recreating it at his end. It's Alice who is sending the bits. Yes, Alice is sending the bits. You see, there is a classical channel in the quantum circuit. Second one is, say, Alice has sent through a classical channel 0, 1 to Bob. So that means 0 and 1 means what was there? What was there? alpha 1 plus beta 0. So Bob will do what? Bob has received what? Alpha 1 plus beta 0. So simple, Bob will apply what? X get. X will do what? It's a simple NOT get. So just flipping the steps. So it will make it alpha 0 and it will make it beta 1. Again, recreating successfully through just one get. So one NOT get. Third one is, say Alice has sent 1 0 to Bob. What was my state for 1 0? It was alpha 0 minus beta 1. Can anyone tell what? Yes, absolutely. So it was alpha 0 minus beta 1. So Bob will do nothing but applying a phase gate. Phase gate does what? If it is 0, it does nothing. So it's alpha 0 itself. And if it is 1, it makes it minus 1. So that minus and this minus will ultimately be cancelled out and it will be beta 1. Again, successfully recreating that state that's supposed to be received. Fourth one is what? The Alice has sent 1 1. This classical information to Bob. Now, what Bob has received initially? Alpha 1 minus beta 0. That means what? First, if I apply X gate, say, it will give me what? Alpha 0 minus beta 1. Now, if I apply another Z gate, it will do what? We keep it alpha 0 minus of minus, which is plus beta 1. Again, successfully recreating the state. So at the end, we have achieved, what we have achieved is Alice and Bob both have started with a state alpha 0 and beta 1. And ultimately, Bob is able, through some quantum operations and with the help of a classical channel, right? So through some quantum operations and with the help of a classical channel, right now, Bob is able to get that state fully at his end, and that has not been said. Quantum states, we cannot send a quantum state, rather we say that we teleported the quantum state, which is nothing but recreating the quantum state at some other end. So this is a basic quantum teleportation process. Now, there are two questions that you can ask. So kind of now 2 questions you can ask. Yes. And this library, that what we will be applying based on what? That has to be pre-shared with Bob. Because Bob has received alpha 0 plus beta 1. But what if it is not the desired one? So Bob will not understand that, right? But whenever Alice will be sending 0 0, that means 0 0 is a signal that Bob has not to do, need not to do anything. That library definitely should be there. Now, 2 questions you can have on mind. The first question is how much it is realistic. That is, one question is, say we have never said that how far Alice and Bob can be. Just like the entanglement, everything. Here also the kind of that logic might come. So if Alice and Bob are really separated by a long distance, does it really mean that they can able to teleport? Theoretically, yes. But now the question is, someone asked this question in QT-02 first class. Okay, first class of this session. That is it really practically doable? And why we call it practically doable, though theoretically it is, I was telling that it's not possible. Today we'll be getting that answer. So, even though we call it that even if it is separated by a space-like distance, then also we ultimately can teleport. This idea is against the theory of relativity, which states that nothing can be faster than light. But here, if it is separated by a space-like distance, it has to be faster than light. But the real answer to that thing is this thing. Just check the circuit. You are using a classical chart. In classical world, definitely nothing can in practice be separated by a space-like distance. So if you're able to do that, you are also able to do the quantum teleportation as well. So the answer to that is It's a theoretical concept. So ultimately, since we are incorporating a classical channel, so it obeys the theory of relativity. Okay, that was the first thing. So I'm not writing the question, I hope. So space like distance, just writing a few points, though it's a space like distance. Then what about the theory of relativity? Is teleportation faster than speed of light? Answer is the classical communication channel. Okay, just like this. Keep it in mind. And the second one is there any cloning done in teleportation? Do you really think that I have cloned or there is any concept of cloning? The answer is again no. So there is no cloning. Though it seems like alpha 0 and beta 1 was an arbitrary quantum state where Alice also does not have any precise information on the values of alpha and beta. But ultimately at Bob's end, Bob is able to get this particular quantum state. So you might be having some doubts that whether there is any, can we call this a cloning thing? No. The answer is there is no cloning done in teleportation. We have also seen that there is a cloning concept, but rather what we have done is we have simply recreated. So we have, what's a Bob? Z means Bob has recreated the quantum state. At his end. What is the time now? Anyone with 340? Great. Thank you. Thank you. So here I want to give 1 minute of pause if you are having any question. Nothing here is flawful. Nothing is flawful. It's absolutely experimentally proven. Everything is perfect theory and they are doable. They are absolutely doable. Whenever there is a classical communication channel, you can understand that it has to be realistic. So it obeys the theory of relativity. Okay, so no cloning and teleportation is absolutely clear to all of you. Yes, okay. Thank you. That you decide. One has asked a question that means ultimately at the end, the Alice state will not be there with you. You have to understand it. You please, decide from the measurements that we are getting. Does it seem like that? That is how the qubits are getting. See, this is called quantum state evolution. You are starting with some qubits, then you are entangling some of the qubits, applying a few operators in order to get your output. That is the thing. So where exactly at the end Alice is holding, you have to check that with respect to the qubit from where it was initially alpha 0 plus beta 1. Is it really right now that one? If it is the thing, then it will be, but I don't think that is the case. Just check. Just when Bob has this state, what is the thing that Alice is holding? Yes. So here we have started with 3 qubits, where 2 qubits, 2 and 3 were entangled, and first qubit was a superposed state. Okay. Now, let me go to the next one. That is a dense coding or super dense code. Okay. One thing I want to tell you. If today we do not get much time to get into the depth of this dense coding, just like we have done in the absolutely detailed way we have seen it, like the teleportation, since these topics are very much related to the concept of cryptography, and we will be having few classes on cryptography, we will be covering that. But for your exam purpose, I will definitely have kept that thing in mind. But do not think there is a question from dense coding. Definitely there. Okay. But the derivations, if I am not able to do today, that is kind of an idea. If 15-20 minutes more is required or half an hour is more required, we can far away how it will. Don't jump into the things. That's a different thing. Decoherence is a different stuff. Okay. So on that note, we will be doing it. But first, you have to understand the idea. So what is a dense coding? And it is also alternatively known as a super dense coding. Okay. So the idea now is kind of reverse. So in teleportation, what we have seen? In teleportation, we have seen that ultimately a quantum state is supposed to be transferred or teleported at another end. But for that, we are taking help of some classical communication channels. So we can call it in this way that ultimately some classical bits are actually being sent in order to create a quantum state. Because I'm not sending the quantum state, but I'm definitely sending those two bits like 00, 01, 10, 11. So the idea of teleportation is I'm actually sending few classical bits in order to get or in order to create the quantum state. Whereas the idea of super dense coding is exactly the reverse. It says that you have to actually, in order to get some classical bits, you actually have to send some quantum bits, quantum state. Now, through the interpretation of the quantum state at Bob's end, Bob should now be able to predict that what was the classical information that Alice wanted to transfer. That is kind of an idea. So basically, let us now start. So the idea was all the slides will be shared, just like the earlier class, definitely. Again, if you want some hardcore theory, not this much of detailed mathematics, you are not going to get anywhere, I guess. I mean, definitely you'll be getting, but all the things, what are all the kind of how to understand those two math lines, that is also going to be a challenge for quantum. So, but for the theory, for the detailed elaboration, don't really rely on these, only these PPTs and all. Please go through some very standard books. This is for your understanding. Okay. So Alice wants to send, but these slides, if you're referring, I'll definitely be sharing. Now say, idea is Alice wants to send in this case 2 bits of information, 2 bits of classical information. Zero, 01, 10, or 11. And to do that, Alice is using quantum state. So it's kind of a quantum to classical mapping, whereas teleportation was a classical to quantum map. Another point is that Alice will be sending 1 bit of quantum information. Here, Alice will be sending 1 bit of quantum information, and Bob should be able to extract 2 bits of classical information, right? So, Alice will be sending 1 unit of, or say 1 bit of quantum information through the quantum state, but Bohr should be able to extract two bits of classical information. So that is why, since from one, ultimately you have to extract two bits. So this idea is called coding or a dates coding. Some equivalently you can think of like a encoding, decoding circuit and all that kind of encoder decoder. Now again, we have to use an entangled state in order to achieve this. So starting point is again one of the Bell states. So starting point for this as well will be the entangled Bell state. So the general idea, or say algorithm flow, whatever you say, algo flow, is kind of that. First, out of the entangled Bell state, one qubit will be with Alice and one qubit will be with Bohr. That is the starting point. So first, out of the, there will be an assignment, right? So out of the Bell state, which is entangled, assign one qubit to Alice and one qubit to Bohr. Okay. Point number two is Alice will now do certain computation on hard part of the qubit, which is the entangled one. And that modified qubit or the evolved qubit, Alice will be sending to Bohr. Through the quantum now, since it is a quantum thing, just hold on for some, give me some 10, 15 minutes, Akash, I got your question. I hope it will be again clear. Yes, it is. Yes, it is actually just the reverse process of teleportation. In teleportation, we were actually sending some classical information through classical channel to recreate or to create some quantum state at Bob's end. Here, it's just the reverse process. Alice will be sending some quantum state through some quantum communication channel. Okay, and Bob will ultimately on receiving that quantum thing, quantum state or modified quantum state, Bob should be able to do some maths on her or on his part and able to tell that what was the original intent of Alice. That should be reflecting in the modified quantum state. From that reflection, Bob will be getting whether it was 00, 01, 10 or 1. You might be asking that why this is at all required, why can't I directly send it to Bob? Because it is a part of the quantum communication. Whenever there is a quantum communication, you can require this particular situation to happen. Okay. So second is Alice will now do certain operation on hard part of the qubit. Okay. Third one is Alice will send the modified Is there any issue? Okay, visible. Okay. Thank you. I thought there was an issue. Thank you. Yes. So Alice will now send the modified qubit to Bob. Now, since it is a quantum bit, Alice will be using a quantum channel. That is kind of the idea. And fourth one is what? Now, Bob, on receiving the modified qubit from Alice, okay, along with the original part of the qubit that Bob already has, from where I am getting that? Because from the entangled pair, one was given to Alice, one was given to Bob. So Bob already has that one. Along with the modified qubit, which was a part of the entangled qubit initially at Alice's end, or Alice has done some modification, and that modification has been sent to Bob. So Bob right now has two different set of quantum information, right? Now Bob will be doing some measurements on his part of the qubit. And based on that, he will be able to, within double quote, infer that what classical 2 bits of information has been sent to him. So the idea is here now, why I'm doing it this way is because so that after that, if at least today I end with writing the quantum circuit for this dense coding, you should be able to understand it from the very beginning, because we have very detailed way we have seen how the teleportation works. Okay. So Alice will be having this thing. Okay. Now Bob, on receiving, say, modified qubit information, let me just mark it 1. Okay. From Alice, and along with is part of qubit information within record. I'm writing just 2. Okay, 1 and 2, because Bob has 2 parts of quantum information. So this is a part of the entangled pair. Okay. Now Bob will do certain measurements on his part of the qubit to predict, or say infer, not predict actually. Predict is something where it can be correct or not. So the one is not predict, rather to infer or obtain what classical 2 bits of information Alice wanted to transfer or communicate through. Okay. Therefore, now let me just draw the circuit. So initially it's this thing. It's with Alice. This Hadamar. This is nothing but the Whale state generation. Please show previous slide. Yes. Okay. So this is what? This is just to create the Whale state. Hadamar followed by a CNOT is nothing but a Whale state. It's a basic unit of entanglement. Okay. The Whale state generation section. After that is done, so now it will be your, so this is size A. Now It has to, okay. Yes. So now it has to be some unitary operation on at least this part of the qubit. And why it is unitary while writing it this way? Because it was a quantum state. And here it is a modified quantum state, Q state, Alice's part. I hope you are able to map that how I'm just building the circuit. Then this thing. Then from here it's a written over here. Let me drag it a bit more. So now it will be a CNOT gate here and are followed by a header mode. This is just the undo thing. Okay. I'm undoing it. And because it's for quantum, it's a reversible thing, just like that. And this is a quantum channel. So this is a quantum channel. Why quantum channel do we need? Because we are ultimately transferring what? The quantum state. So in order to transfer the quantum state, we cannot really use some classical communication channel. And this part is known as this is the Bell state measurement thing. So this is generation, this is the quantum channel, and this is Bell state measurement. And what is your U? Your U is nothing but a unitary operator that does certain quantum operations that can be anything on the Alice's part of the quantum state. Okay, and in this part, if anyone has any doubt, this was 0 and 0. On this, I'm applying Hadamard, so it will become K0 plus K1 by root 2. And this was as it is. I have not done anything on this. The purpose here is not for the, see, the purpose of superdense coding is completely different. So for cryptographic context, for the eavesdropping thing, just remember the no cloning and teleportation part is misconfused. So definitely here, this is just the superdense coding thing. But no, because of no cloning, it is of course safe. There is nothing wrong here. Even if I send a quantum state through any channel, so even if some eavesdropper wants to tamper the quantum state, he has to enter into the quantum channel. And if he tampers it, then the quantumness itself will be ultimately lost. Right? So when we will be doing the quantum key distribution and something quantumly is going, we will understand it in even a detailed way. But this anything, if it is quantum, then it of course is not under threat by any eavesdropper. Only threat is in classical. Whenever it's a quantum particle, a quantum state, a quantum communication channel, which is actually holding some quantum thing, then because of the inherent property of no cloning of any quantum particle, even if eavesdropper catches that one, that will be understood by the Bob or say intended receiver. They will simply discard it. So I'm not telling that availability will not be there. It will be available, but it will be detectable. So what is attack? It's not the only the first bit. If it is affected, then of course the presence of an eve or an eavesdropper, that will be very well detected. And those also who know the classical communication and all these things, we all know that we never actually send only the original bits of data. We somehow send some additional bits, which may be some redundancy bits or something, so that our real data gets protected. Similarly, in quantum also we do that thing. So in order to, even if it is 4 times and some additional thing for QKD, for say quantum information, we'll see all those things, everything, why 4, everything we will see. But if it is quantum, it is not breakable. Okay. So this is K0, 0 and 10 by root 2. Now CNOT. So this will become 0, 0 plus 1, 1 by root over x cube. And this is where, till this part, this is say T1. So at T1, we are here. After T1. So this is the schematics of the quantum, this circuit, what? On the super dense coding circuit or dense coding circuit. What is the time now?
It's 4-4, ma'am.
4-4. Anyway, I guess we need 20 minutes approximately to cover it. So we can do it whenever we will start with quantum cryptography. And what I will do is, you at least remember the idea, then we will start with the circuit again, from exactly where we are stopping it. Until this part only will be there in your exam. Don't worry about that. But even this is a circuit, the theory part, that is over. There is a certain maths to confirm that yes, actually, you can. I will be telling portions. So actually, you can see that you are able to do some maths and able to predict that what was your classical 2 bits of information. Okay, I want to pause here. I guess that is okay. So anyone has any doubt? Okay, first of all, in exam, I guess you are asking what will be the things. I already shared it. So it will start with all the linear algebra part that has been covered. First, initially, in day 1, we covered a bit of the generic theory for the classical versus quantum, all the reversibility, explosion of the possibilities and all those stuff. Okay, that will be there, followed by all the math concept, orthogonality, orthonormality, Hermitian operator, everything, inner product space, outer product space, all those stuff. Then block sphere, not much, at least a little bit of that. Block sphere, I guess we have not covered. So, okay, the block sphere, ignore that. So it will then be all the detailed of the quantum mechanical postulates like superposition, entanglement, quantum measurement, where we have seen the projection operator and all those stuff. The probability and probabilistic amplitude conversion stuff. Then it is this thing, today's class, what we covered, no cloning theorem and no cloning, teleportation, and the theory of the super dense coding. There will be, again, I'm repeating, there will be 20 questions, 15 MCQ and 5 multiple select types, where in MCQ, there will be only one answer that is correct. But in multiple select type, there can be more than one answer there that are correct. So you have to mark all of them. That is the quiz details. And concept-wise, any doubt from today's class? Or is it okay? Stopping sharing.
Thank you, ma'am. So,
Okay.
I guess as of now, there are no queries. So in the next session, we'll be able to answer